Designing experiments. Experimental units are the individuals on which the experiment is done. When the units are people, they are called subjects. A treatment is the specific experimental condition applied to the units. For example, say we're testing effects of different vitamins on health. The vitamins would be the treatment. Factors are the explanatory variables in an experiment. Suppose with the vitamins we're testing vitamin E versus vitamin C. Then we would have two factors. Note that factors may have several levels. For instance, different dosages for each type of vitamin. A placebo is a dummy treatment that can have no physical effect. When subjects respond to a placebo treatment, we call this the placebo effect. The fundamental principle of experimental design is control. Control refers to the steps taken to minimize the effects of extraneous variables. There are three fundamental principles of control: comparison, randomization, and blindness. Within blindness, we can have a blind test where the subjects don't know the treatment that they are being given, or a double-blind test where both the subjects and the administrator of the treatments don't know what they are given. Replication, or assigning a treatment to many units, is also very important. This will lower the variability of our outcomes. A confounding or lurking variable is a variable that is not accounted for that correlates with our given variables in the experiment. A control group is one way to manage the effects of lurking variables. A control group is a group that receives no treatment. We use it for comparison. Using good experimental design should help you with causation, control, and variability. Some types of experimental design include completely randomized design. In completely randomized design, subjects are assigned at random to groups. Randomized block designs. In randomized block design, subjects are divided into homogeneous blocks before they are assigned randomly to treatments. Matched pairs design. This is a special case of randomized block. It works best when we have two treatments and the subjects are grouped into pairs. An observed effect is statistically significant if it's too large to attribute plausibility to chance. We must always watch for hidden bias, confounding variables, and be careful with lack of realism with our treatments. Let's look at some examples. Example 1. The editor of a magazine is wondering if the type of font used in the articles affects the reading speed of the subscribers of the magazine. He asks 10 subscribers to read 4 articles, each with different fonts. If the reading speed increases with a particular font, he will use it in the next publication. Is this an experiment or a study? This is an experiment because we're assigning the treatments of reading the articles. If this is an experiment, is it randomized or block design? Well, he has the 10 subscribers reading the 4 articles. It is randomized. They are not blocked. If this is an experiment, identify the explanatory and response variables. The explanatory variables would be our type of font. And the response variables would be our reading speed or length of time to read an article. If this is an experiment, draw a diagram representing the levels and treatments. Well, when we're drawing a diagram for an experiment, we start off with what's going in, how we're going to split apart people or do what we need to do, and we're going to end it with a comparison. Now we have 4 different fonts, so I'm going to make 4 branches. We have 4 treatments, and each of those treatments will be reading a different font, and then we're going to compare our reading times for each of these fonts. So we start off with our 10 subjects, and each one's going to read a different font. So this would be, first treatment would read article with font A, and then we'd read an article with font B, read an article with font C, and read an article with font D, and then we would compare reading times. Example 2. Many colleges and universities have developed calculus reform, courses which substantially alter the way the calculus is taught. The goal is that the reform courses help students to understand fundamental calculus concepts better than traditionally taught courses do. If you simply compare scores on standardized calculus tests between students in the traditional and the reform classes, would you be able to conclude that any differences you might find are attributable to the teaching style? Well, in this situation, we really need more information. For instance, are we looking at students at the same universities or different? And what type of background do the students have? If we're comparing standardized forms of standardized tests, that's good, but what about the actual teaching techniques used between the calculus classes? Are there the teachers that we're comparing, do they have the same kind of background, etc.? Describe how you might design an experiment to assess whether the goal is being met. Well, we'd want to get groups of similar students and be able to compare those similar students with similar abilities in order to see if the outcome's being met. So probably choosing an equal number or very close to the same number of students within the same university, have teachers that have the similar backgrounds, similar teaching styles, using each of the different techniques on the students, and make sure that they all have a common final exam.